Let's now recap our curve sketching menu, because drawing graphs can be sometimes a good way of looking at those inequations. First of all, rewrite the function as one complete fraction. So if it's one of those ones where it's, x plus 4 on x cubed or something like that, rewrite it as one complete fraction. If you want to find your y-intercept, that's always the easy one to find because we just substitute in x equals 0. And then if you want to find x-intercepts, then we want the numerator to equal 0. Do a polynomial division, because then that can give us even more information. Remember our polynomial division, p of x on a of x, we'd end up with a quotient plus the remainder over the divisor. And when it's in that form, we know the bottom of the fraction can't equal 0, so that tells us about vertical asymptotes. The quotient will give us the horizontal or oblique asymptote, depending on what that quotient is. And then on the top, our remainder will tell us whether or not the curve cuts that horizontal or oblique asymptote, so if that one equals 0. Finally, symmetry, if you notice any. Now, you might not notice it, but if you do spot it, it can save you time, because if you notice it's an odd or an even function, well, technically you really only need to draw half of the graph, because then you reflect it in the appropriate direction and you've got the other half of the graph. The other symmetry to watch out for is the one where y equals x. So if you can change x and y around and you get exactly the same function, that means it is its own inverse, which means it must reflect in the line y equals x. That one's not as easy to pick up straight away with some functions. But if you do notice it, then that's another thing you could use. Now, a bit of a mention about asymptotes in general. Vertical asymptotes. They're the exclusions in the domain. Bottom of the fraction can't equal 0. Curves do not touch them because they are exclusions in the domain. So therefore that x value is not in this function, so it can't touch that vertical asymptotes. It's why we draw asymptotes with a dotted line rather than a solid line. So when we're doing our graphs, that dotted line indicates this is not part of the solution. This is not part of the function. Horizontal ones, that's where functions might converge to a specific value. Curves can touch horizontal asymptotes, and oblique asymptotes for that matter. There are 3 limits. Well, there's more than 3, but there's 3 special ones we like to look at which can affect the value of these asymptotes. It helps us. This idea, hyperbola. We know that our hyperbola, when we go out to positive or negative infinity, that curve's going to be approaching 0. So we know that limit. This one, our backwards exponential. So e to the power of negative x. We know when x approaches infinity, that will approach 0. And then on the flip side, the regular exponential, as that one's approaching negative infinity, that would approach 0. So how can that help us? You might recall things like this, where we had to find this limit as x approaches infinity. Well, the long way of doing it is to think about it using this idea of 1 on x. We know the limit of that 0. You divide everything by the highest power. So if I divide everything by x squared, I get 1 plus 0 on 0 minus 1, because the x squared on x squared, that's 1. The x on x squared is 1 on x, we know that approaches 0, and so on. In reality, with these sort of ones, because we know that's going to happen, you just look at the highest power, and it's the coefficients of those that will end up being. So we get negative 1. Something like this. If I wanted to investigate this function, e to the power of x plus e to the power of minus x over 2e to the power of x, as x approaches infinity, what I would like to do is rewrite this fraction so that all of those exponentials are to either a negative power or a positive power. Now, which one to pick comes down to where am I investigating. So if I'm investigating x to approach infinity, then I would like it in terms of the negative power, because I know that limit will go to 0. So what can I do here? Well, I can divide everything by e to the power of x, positive power. So whatever the highest positive power is, I'm going to divide everything by that. That will leave me with a situation where the only exponentials now have negative powers. And I know as x approaches infinity, that's going to be 0. So therefore that must approach a half. It must converge towards a half. That same function, if I now want to know what's happening at the other end, at negative infinity, so it's the same function, but But now I would like everything in terms of a positive index, because that's the limit I know here, if I want to invest negative infinity. So this time I will divide everything by e to the power of negative x, and I end up with this. E to the power of 2x plus 1 on e to the power of 2x. I know those e to the power of 2x's will approach 0, so I end up with 1 on 0, which is undefined, or another way of thinking about undefined when we're talking about our graph is that one must be going off to infinity itself, the y value. Let's do an example. We're going to sketch this simple little one, x cubed minus 9x on x squared minus 4. We've got to find our asymptotes and where the graph meets the axis, in other words the intercepts. The y-intercept, x equals 0, always the quick one to do, so we do that first. It's going to be, well, it is 0, isn't it? Now let's find the x-intercepts. Solving that one, we get 3 x-intercepts, 0, which actually when you think about it, we already knew that one, because this is telling us it goes through the origins, because if the y-intercept is x equals 0, it's going through the origin. So consequently we're expecting to find that as an x-intercept as well. But the other ones we get is plus or minus 3. I know those 3 points. Now, looking at this, if I do my polynomial division, I'll get x minus 5x on x squared minus 4. I know I've got a vertical asymptote when the bottom of the fraction equals 0. So we've got 2 of them at plus or minus 2. Okay? Let's put those in. But we're going to have, in this case, an oblique asymptote at y equals x. Does the curve meet that asymptote? That's when I look at the top of the fraction. Is it possible for 5x to equal 0? Well, yes it is. That's at x equals 0. And again, we probably knew that already because we'd already determined that the origin was an x-intercept. So we actually knew that one already. Okay, it's an odd function. So if I look at that, it's going to be an odd function. How do I know that? Well, the top of the fraction is an odd function. The bottom of the fraction is an even function. So if I've got odd divided by even, they're different types of functions, therefore the whole function must be odd. Or if it's the same type of function, so if they were both odd or they were both even, we know it would produce an even function. If they're different types of functions, we know it's going to produce an odd function. Okay, it's got rotational symmetry, we know that. Now we're going to draw our sketch. We know things like bending towards asymptotes, passing through intercepts. It would end up looking like that one. Okay, we'll add that to our list.